Okay, so when we start with chapter 5, we're going to be doing something called approximating area, which we start off with these first examples. These first two examples are going to seem very trivial, and you may not know where we're headed with them, but you will see by the end of example 3. So first one, it says train moves along a track at a steady rate of 75 miles per hour. Like I said, this first example is going to seem very, very trivial. Traveling from 7 to 9, what is the total distance traveled by the train? So you think like very, very simple example that we're looking at here. This is kind of a physics sort of application that we could make. So here's just a quick little formula that I'm going to write down for you. If you are trying to find distance traveled, and you know how fast the thing is going, and you know how long it's traveling, it's a very, very easy formula. Distance traveled is just the velocity, so however fast you're going, times the elapsed time. Okay, so for us, it's going to be super, super easy. They're going 75 miles per hour. And then times 2 hours. So what ends up happening, we can do this dimensional analysis that I've talked about with the units. So you have per hour times hour. Those two end up canceling each other out. And then your units that you're left with are just miles. So we multiply together. We end up with 150 miles, which, like I said, probably seems like a pretty trivial example. But what I want you to look at is a velocity curve. So if we graph a velocity curve for this example, we've got, this is t for time, this is velocity. If we just do, let's do 25, 50, 75, our velocity curve just looks like that. Just a constant velocity, and then we're going to look over a 2-hour time interval. So let's say we go like 1, 2, 3, 4, 5, 6, 7, 8, 9. So what we're really actually looking at is the area under the velocity curve over that change in time. So if we say this is 7 and this is 9, what we're actually finding, like I said, is the area under the velocity curve. If we find the area of that little rectangle, then we get the total distance traveled. And this is a 2 by 75 rectangle. Multiply that together, we get our 150 miles. So here's the application that we're going to be working with for this section and beyond. If we try to find the distance traveled, from this point forward, we are going to think of it as area under the velocity curve. I guess let's say under the velocity graph, because obviously in this example it is not a curve. So we think of distance traveled as the area under the velocity graph, and then of course time, we use that as our left bound and our right bound. All right, so let's go on to a next example. I'm going to make up a new graph for this one. So what if our velocity changes, but it's still constant over certain intervals? So same thing, and this I'm just making up for you right now, so you wouldn't have known what this graph looked like just based on the question. So velocity and time. So let's say we have 1, 2, 3, 4 hours passing. Let's edge this up by 20. So let's say 20 miles per hour, 40, 60, 80. So let's say for the first hour, you're traveling at 30 miles per hour. All right, and then we're going to jump up to 60 miles per hour for the next 2 hours. And then for the last hour, we're going to go down to 50. Okay, so that's our velocity graph. So like I said, we're going 30 miles per hour, 60, and then 50. And I'm totally making this up. You would have had no way of knowing those velocities just from reading the equation. So our distance, like I said, we're treating that under the area under the velocity graph. So we want to know how much time has passed in, I guess 6 hours. Sorry, let's extend this a little bit. So let's just say it keeps going. And we'll make that 6. Okay, so in those 6 hours, the distance is just the area under the velocity graph. So this one right here, we can make a little rectangle out of that. Its width would be 1 hour. And then its height would be 30 miles per hour. We take that rectangle and then add it to the next rectangle, then plus, and we make a little rectangle out of this one. This one is 2 hours times 60 miles per hour. and then plus, then we go with the next rectangle. And this is 3 hours times 50 miles per hour. Okay, so we calculate this. In the first hour, we went 30 miles, plus in the next 2 hours, we went 120 miles, plus, and then in the next 3 hours, we went 150 miles. So add that all together, we end up with 300 miles. And that would be your final answer. So like I said, you can get this visual of it being area under the curve. So like this rectangle had an area of 30, this rectangle had an area of 120, and this rectangle had an area of 150, and you're just adding them all together. Okay, so that's the exact distance that the car has gone in 6 hours. Okay, so now let's see, perhaps we don't actually travel in perfect rectangles, which is unlikely. This would be like cruise control for a straight hour, then 2 hours and 3 hours. It's not really how velocity typically works. So let's say that particle starts at 0, moves along the x-axis with this velocity. Where is the particle at t equals 3? So it looks something like this. So velocity curve, time, same as before. And if we move with a parabola like this, okay, so it's going to look something like that. So we want to know how far the car has gone in 3 hours. So if we say 1, 2, 3. So what we are looking for is still the area under the velocity curve. So we are looking for this area right here. We're trying to approximate it. So based on what we know so far, what we actually end up doing is we estimate the area the best we can. Okay, so the goal is we are going to estimate using rectangles. Okay, so here's what ends up happening. We slice up our interval however much we want. You know, we can slice it into half units like this. So we do that, slice it up. And then we've got options, and we're going to talk about all 3 of those options. We could use this point and make these your rectangles. Okay, so use those rectangles. If you use these rectangles, then your estimation is a little bit too low. That goes under the curve. We could use the right endpoint and make rectangles like this. And then, of course, if we do that, our estimation is a little bit too high. So as I'm assuming you could imagine, the best way to go is to do the midpoint. So what you do is you take the midpoint of each interval, make a rectangle out of that, and now this rectangle is actually a pretty fair approximation because this little bit that's too high almost balances this little bit that's too low. So we've got a third option called the midpoint that runs right through the middle like that. And it's a pretty good give and take of like the balancing the too high with the too low. Okay, so that's our goal. That's what we're going to start with on the next page. So we've got 3 different things that we can look at here. We've got right-hand sums, left-hand sums, and midpoint sums. That's basically what I just wrote out. So 2 pictures. So we're going to sketch out that exact graph that we were just looking at. So sketch it out 3 times. Same parabola. I'll do my best to make them approximately the same. Okay, so again, just really quickly, that right-hand sum, if we split it into however many intervals, and you'll be able to change problem by problem how many intervals you're going to use. If you use a right-hand sum like this, so right-hand sum means between this endpoint and this endpoint, you take the function value on the right. Okay, so it looks like this. My rectangles would look like this. Okay, and like we said on the front, it's going to be an overestimate. Okay, so this approximation is too big. Too big. Okay, this one, if I go from the left, so same thing, I'm going to split up into a bunch of different intervals. If I use the left endpoint, it's going to go right under my curve. And so if I'm using the left endpoint, these are my areas that I'm counting right here. And in this case, my approximation is too small. feel like this is turning into like a Goldilocks and Three Bears situation right now. So we've got this will be too big, this will be too small, and the midpoint sum is just right. Okay, so same thing, we're going to split this up into however many intervals we want, and it's going to change problem by problem. We'll get to notation just below here. So we go in the middle of the interval and use that to make a rectangle. Okay, so when we use those, like I said, the part above kind of balances with the point below. This is the most accurate that we have. Doesn't mean that it always makes the most sense to use, and we'll understand that more as we go through. All right, so here are some notes. So a right-hand sum. A right-hand sum is not always an overestimate. The only reason it's an overestimate here is because I have an increasing function. If I had a decreasing function, it would actually underestimate because the point on the left would be smaller than the point on the right. I'm sorry, if you were decreasing, the point on the left would be larger, so the point on the right would be smaller. So it all depends on whether your function is rising or falling, increasing or decreasing. So a right-hand sum overestimates if it's an increasing function, but if you flip the graph and picture like what a decreasing function would look like, the right-hand sum would actually underestimate in that case. So it all depends on which you're trying to accomplish. Okay, so right-hand sum overestimates an increasing function and underestimates a decreasing function. A. Okay, and then the opposite is true for a left-hand sum. So a left-hand sum underestimates an increasing graph and it would overestimate. So picture like this. If you're using a left-hand sum, that would go over if it was a decreasing graph, like that. Okay, so a left-hand sum underestimates an increasing graph. And overestimates a decreasing graph. Okay, so that will change problem by problem. The AP test loves to ask, like, oh, is this approximation too large or too small? And it will all depend on which approximation they asked you to use. Okay, so some notation that you'll see in the book looks like this. They will have R sub n, L sub n, and M sub n. Obviously, R, L, and M stand for right, left, and midpoint. N equals the number of rectangles that they ask you to split up into. So like this one, for instance, would be 1, 2, 3, 4, 5, 6, 7. That would be an M7 because I split the interval up into 7 rectangles. The main idea with these is that the more rectangles you use, the more accurate the approximation is going to be. All right, and we'll get into that a little bit on the next page. So we've got a chart, represents velocity at 2-second intervals. We're going to compute a bunch of these. So R6, so if you look here, we've got 1, 2, 3, 4, 5, 6 intervals, you know, from 0 to 2, 2 to 4, etc., all the way down from 10 to 12. So when we compute R6, what we do is we treat, you know, here's your 6 different widths. Okay, so what we're doing is we're just adding up all of these rectangles, the area of all of these rectangles. So you have base times height. So for an R6, for instance, your first rectangle will have a width of 2, just because it goes from 0 to 2, so that's the width. And then the height that you use would be the right endpoint. So 0 to 2, 2 is the right bound, 7 is the velocity. So you use the function value for the right endpoint. So it would be 2 times 7. Okay, this would be the length of time, this would be the velocity of the right endpoint. Plus, then we go into the next rectangle. This rectangle goes from 2 to 4, so the width is still 2. And then we use the velocity for the right endpoint, which is 9. Okay, that's the second rectangle. We've got 6 of these. Plus, then from 4 to 6, the width is still 2. and we're using the velocity of the right endpoint, which is 14, plus fourth rectangle from 6 to 8, our width is still 2. We use the velocity at 8, which is 21, plus fifth rectangle from 8 to 10, the width is still 2, and we use the velocity at 10, which is 10, plus finally from 10 to 12, the width of that interval is 2, and then the right-hand velocity is 15. Okay, so you would have a calculator just to add all these up. So plug these in, you get 14 plus 18 plus 28 plus 42 plus 20 plus 30. That ends up being 152. And your units, since you're multiplying seconds times meters per second, your units would end up being meters. And that would be your final answer. Now for this one, we actually have no way of knowing whether it's an overestimate or an underestimate because it's not increasing or decreasing the entire time. And we're in a table, so we don't make assumptions about whether, like, it might decrease in between here. We just can't see what's happening. Okay, now M3. From 0 to 12, we're going to split it into 3 intervals, which means we're going to go by 4 seconds. So here we're going to go from 0 all the way to 4, then from 4 to 8, and then from 8 to 12. Okay, so an M3 means we're going to use the midpoint. So first rectangle, we're going from 0 to 4. The width is 4. It's 4 seconds long. And then when we go from 0 to 4, we use the middle velocity, which is 7. Plus second rectangle goes from 4 to 8. That width, of course, is 4. Our middle velocity is 14. Plus, and then our last one from 8 to 12, that width again is 4, and our middle velocity is 10. Okay, so we would multiply these, add them all together, so we had 28 plus 56 plus 40. We add that all together and we get 124 meters. Okay, so remember, these are supposed to be approximating the same quantity. All of these are trying to figure out how many meters our particle went over this 12-second interval. Okay, so let's look. We have 2 more over here. Okay, so we're computing L6. Okay, so L6, we're going to kind of flip back and forth here. I'll actually put this right up on the screen for you. So put this up above. Printed out a second page so we could still see the table. All right, so it looks like that. So we're splitting up into 6 intervals. So for the whole 12 seconds, that means we're splitting up into 6 2-second intervals. So our first interval, of course, is 2 seconds. Then from 0 to 2, we're using the left velocity, which is 0. Plus, from 2 to 4, we use the left velocity of 7. From 4 to 6, we use the left velocity of 9. From 6 to 8, left velocity of 14. From 8 to 10, left velocity of 21. Plus, and from 10 to 12, left velocity of 10 is the one we use. Okay, so this whole thing would just get plugged right into a calculator. So we would have 0, and then plus 14, plus 18, plus 28, plus 42, and then plus 20. So for some reason I didn't calculate that before, so let me plug it in. So 14 plus 18 plus 28 plus 42 plus 20. That comes out to be 122 meters. Okay, so that's pretty similar to the M3 that we got. So finally, let's calculate an R3. So R3 is a right sum, but going over 3 intervals. So we're going from 0 to 4, 4 to 8, 8 to 12. So first interval goes from 0 to 4, and we're using the right endpoint, which would be 9. Plus, then from 4 to 8, we use the right endpoint, which is 21. Plus, and then from 8 to 12, we use the right endpoint of 15. Okay, so one more time, plug these in. We've got 36 plus 84 plus 60. And that comes out to be 180. So that one's pretty big. Here's the very important thing to remember. These are all estimates of the same quantity.